Good afternoon. We want to talk today about solving inequalities. Our objectives are to be able to solve one, two, and multi-step inequalities, to graph the solutions to an inequality, and then a third objective that's not listed here is to talk about interval notation. We'll talk about interval notation today, but it will be something that we come back to again quite a few times before the end of the chapter. When we solve inequalities, the work of solving an inequality is almost identical to solving an equation with two major exceptions. Those two major exceptions are these. The first, the solution to an inequality is a set of numbers rather than a single value. When we solve an equation, we get an answer like x equals 2. For an inequality, we get something more like x is greater than 2, which is a whole set of numbers on the number line. The second important thing to remember is that anytime you multiply or divide by a negative value, any negative number, you have to switch the direction of the inequality. Switch the direction of the inequality. This is true for multiplication and division only. It is not true for addition and subtraction. You can add and subtract any negative number you want and not need to switch the direction of the inequality. However, whenever you multiply or divide by a negative number, switch the direction of the inequality. So if it's a greater than symbol to start with, change it to less than, and vice versa. When we graph inequalities, since there are infinitely many solutions to an inequality, there are an infinite number of values that are greater than 2, for example, we want to use a graph to show all those possible solutions. So we would graph the solutions on a number line, and we have to make a distinction between, number line, not line. We need to make a distinction between greater than and less than symbols, which get an open dot because we can get up to that number but not include that number in our solution set, or greater than or equal to and less than or equal to. If it's greater than or less than, because the actual value that we're using, like x is greater than 2, 2 is not included in that number set, and as a result, we should not have a closed dot. We're going to show an open dot. The other thing that's going to be important is, as we talk about interval notation, when we've got less than or greater than, we'll use parentheses to show that it gets up to but not including the number, and then brackets to show that it can include the value. So we're going to do several examples, and you'll get to see what it looks like to solve when we have a set of answers, when we switch inequalities, how we graph it on the number line with open or closed dots, and then how we can use some interval notation. So let's take a look here at example number 1. Example number 1 says 4y minus 3 is less than 5y plus 2, and they want us to graph the solution on a number line. So the first thing I'm going to do is solve this just as if there were no inequality, that there were an equal sign right here instead. So the first thing I would do is subtract 4y. I'm subtracting something. As long as I'm not multiplying or dividing, I don't have to worry about that switching the inequality problem. So I've got negative 3 is less than y plus 2. And then I'm going to move the 2 to the other side. So again, I'm subtracting, so I'm not multiplying or dividing. I can't switch anything. So I've got negative 5 is less than y. Now, when I write my inequalities, I typically prefer to have my variable on the left side. So I'm going to switch this to y is greater than negative 5. It's a little bit easier for me to think about. Now, if you want to think back to elementary school when they talked about eating the bigger number, here I want to make sure that I continue to eat the y. Okay, so that's one way to write my solution. This is the set of the answers. Because it is a greater than symbol, I'm going to use an open dot at negative 5. So an open dot at negative 5, and I want to graph in the direction of the rest of the answers. So I want values that are greater than negative 5. So let's use 0 as a test point. Is 0 greater than negative 5? Well, sure it is. So I'm going to shade towards 0. So I'm going to just shade this direction to show that all of the answers this direction are possible solutions. Now that I have the graph, I can also use interval notation. 5 is not an answer choice, thus the open dot. In interval notation, I'm going to use a parenthesis. So I can start at negative 5 and go until positive infinity. Any number to the right on this number line would count. So I'm certainly not going to count. Anytime I've got infinity, it's a number I can't actually reach because it's not actually a number, I'm going to use a parenthesis with infinity. This parenthesis was because of the no equal sign here, and this one is because it's an infinity. So let's try a similar problem for number 2. Again, I want to get all of my x's to the same side, so maybe I'm going to subtract 5x from both sides. I get x minus 2 is less than 7. I'll add 2 to both sides, and I get x is less than 9. Now again, it's a less than symbol. X is less, I'm sorry, I wrote that incorrectly. X is less than 9. I have my variable on the left-hand side, which is what I prefer. I'm going to use an open dot at 9, and I want values that are less than 9. So again, I'll use a test point. 0 is less than 9, so I'm going to shade towards the 0. That's this direction. Now when I use interval notation, from the left-hand side, I'm at negative infinity. That gets a parenthesis because it's infinity. And then I'm going to stop at 9, which also gets a parenthesis because 9 is not a possible solution. If it were, I would use a bracket. Flip over real quick to page 10 for me, and we'll take a look at a couple more examples here. For question number 3, in order to solve this inequality, I need to divide both sides by a negative 0.3. And this is the situation that you need to be aware of. I am dividing in this situation by a negative value. So I'm going to put a star over here because this is an important example to think about. When I divide by a negative number, I have to remember to switch the direction of my inequality. So my answer is going to be something is less than or equal to p. And so in my calculator, I can do 12 divided by negative 0.3, and I'm going to get a negative 40 over here. So I switched the direction. Before it opened and ate the 12, if you wanted to think of it that way. Now it's eating the p. Now, in this situation, I need to pay attention to the fact that, again, I prefer to have my variable on the left side. So p is greater than or equal to negative 40. I continue to make sure that my inequality opens towards my variable in both cases. Now, in this case, I need to actually put some numbers on the number line. So I'm going to put negative 40 here in the middle. Maybe I'll add negative 20 over here. And then I counted out 1, 2, 3. So 1, 2, 3, and call this negative 60. You don't have to be real specific with your number line. In this case, I have the less than or equal to symbol. So I'm going to have a closed dot at negative 40, excuse me. And I want the values that are greater than. And so negative 20 is greater than or equal to negative 40. So I'm going to shade to the right. And then when I read my answer from left to right, I'm going to start at negative 40, and this time it gets a bracket because it has the or equal to and a closed dot. So negative 40, and then it goes to a positive infinity, which gets a parenthesis because I never can reach infinity. Go ahead and try example number 4 on your own. It's very similar to example number 3. To solve, you're going to have to divide both sides by negative 3, which means it's important that you remember to switch the inequality. You're welcome to check that answer on the notes that are posted online. But let's take a look at number 5. For question number 5, I want to find a way to solve for the variable x. So the first thing I'm going to do is I'm going to multiply both sides by 2 to cancel the 2 out here. Multiply this by 2, and I get negative 2x is greater than x minus 7. Well, in order to solve that, I'm going to subtract x and subtract x. And I get negative 3x is greater than negative 7. And then in order to solve this, I have to divide by negative 3 and divide by negative 3. So I get x is less than 7/3. Now notice that I switched my inequality. Because I was dividing by a negative number, I switched the direction of my inequality. So this is part of my solution. I've got a crazy fraction here that I don't necessarily like, but that's okay. I'm going to do 7/3 here. Maybe I'll call this 8/3 about here, 9/3, which is also known as 3, but I can leave it like that. And over here I'll do 6/3, also known as 2, and 5/3. Just makes it something easy to count by. There's no or equal to, so I'm going to put an open dot here. And I want the values that are less than that. So, for example, 0 would be over here. Is 0 less than 7/3? Yes, it is. I'm going to go towards 0. Shade this in. And then talk about my solution. Reading my graph from left to right, I start at negative infinity. Infinity always gets a parenthesis. And I'm going to 7/3. 7/3 also gets a parenthesis because that value is not included in my answer. close the parenthesis. We're going to look at example 6 together in class, so there's no need to do that problem now. If you choose to try that problem on your own, you're more than welcome to do so.